Right, so we're going to do the basics of heat and rotary in this video. Both of these are quite important in Crossroads, and they're the two main power systems. You use them a lot early game, a bit less mid-game, but still quite a lot. And then at the very end, you use them a ton. So heat and rotary power are really the bread and butter of the mod, so it's a good idea to just have an overview. So we'll start with heat. Heat is exactly what it sounds like, it's temperature. So hotter things have more heat, colder things have less. So I'm going to be using this omnimeter, which is a little handy device. If I right-click on something, it gives me information. So it just told me when I right-clicked on this cable, it's this temperature in degrees C, this temperature in Kelvin, this temperature in the biome. So this is the air temperature. And right now, nothing special is happening. And we're not making any heat, we're not using any on this little system. So we're at the air temperature, it's all cooled down. So heat's moved by these cables, these insulated heat cables. And I can actually detach neighboring ones with a wrench. So if we wanted two completely separate lines of heat cables to run next to each other, we can do that. And they're going to balance the temperature. So if I heat, actually no, I should keep that there. So this firebox is a very simple source of heat. It burns fuels like a furnace and just heats up as a result. So if I put some charcoal in, it's getting hotter. We can see in the UI. This cable's getting hotter, and the temperature is just being kept balanced along the cable and with this machine. So this machine is also getting heated up. All right. Now, this firebox is making 10 degrees C per tick, which is getting balanced over like 5 machines. So it works out to 2 degrees C per tick per machine, but that's not really what we're going to care about. We're going to say we're making 10 degrees C per tick. Okay? And this smelter is using 10. Now, if we look at the tooltip, we can see that because it says, well, it's going to run at normal speed when above 200 degrees C, and it's going to use 5 degrees C per tick when it's doing that. Oh, ignore that. Hold on. At 300 degrees C and above, we're going to run at double speed, and we're going to use around 10 degrees C per tick. Not around, exactly 10 degrees C per tick. Right? Now, we just saw we're at 300 degrees C. We heated up there, so we're using the full 10 degrees C per tick. So why did we reach 300 degrees C and stop? Which, as you can see, is what we're doing. We're balanced at around 300. Well, the firebox is making 10. We reached 300. The smelter started using 10, and we were using heat at the same rate we're making it, which is just keeping us steady at 300 degrees C. Another thing to mention is that this smelter, like most heat machines, use heat even when they're not running. Just because it's hot, it's using heat. This thing is like a furnace. It cooks things using heat, and it uses the same amount of heat whether it's actually cooking or not. Now, this might sound wasteful, but it isn't. It's a good thing. And the reason it's a good thing is if I disconnect our smelter, which is right now the only thing using heat, we're going to watch the temperature of this cable. And it's going to take a minute because I used way better cables than I needed to for this demo. These are ceramic heat cables. You'll see that it says in the tooltip melting point 3000 C. So if we give it a minute to just reach 3000, and I'm actually going to speed this up by adding another firebox because I am very impatient. Should be getting close-ish. We want more fireboxes. Is more fireboxes more good? Done. If we're getting very close, the moment that this says 3, we're going to melt. There we go. They all melted. So if you reach the melting temperature of a cable, bad stuff pretty obviously happens. Now these are still burning, so I should probably stop them from running and repeatedly melting the cables as I try and place them. If this actually happened, and you weren't in a creative mode demo, you would wait for things to cool down before you try to re-add cables so they don't immediately remelt. Right? So this thing would keep heating up and keep heating up. This is actually another heat cable for my next demo, which, as you can see, is also overheated. We're getting there. So it would keep heating up and keep heating up until your cable's melted, which is a bad thing. So the fact that we're just have a thing to use up the heat as we're making it is a good thing. And it's also a good thing that this uses more heat the hotter it gets. So that we pretty much, as long as we have enough machines hooked up, we're pretty much guaranteed we're never going to melt, because as we get hotter and hotter, more machines are going to use more and more heat until it balances out. The other thing to note is that there's different types of heat cables. So there's wool ones, there's ceramic, there's slime. No one ever uses slime though. There's ice. There's a bunch of materials, and they all have different melting temperatures. Higher is better, and different losses. Lower is better. Loss is what it sounds like. These cables right now are a little bit hot. They're 190. If I disconnect it, everything, you're seeing the temperature slowly dropping. And that's because the heat is being lost until it reaches the biome temperature. So there's a little bit of ambient loss in the cables. It's usually not a huge effect if you're using good cables and it's not too many of them. But there's a tiny bit of loss, which can also be helpful to make sure that you don't accidentally overheat your system and melt your cables. Now, heat also works the other way around. So over here with the smelter, we wanted heat. Over here, this is another machine, the fluid cooler, which wants cold. So heat cables can also be used to transmit cold, which is just heat but low numbers. So if we use an ice box, which is the exact opposite of a firebox, it cools things using cold fuels like snow and ice. We've cooled down. The ice box can't get very cold. It's a pretty simple machine. We only get to around -20. We've cooled down this cable. Now, cables never break by freezing. They don't have like a cold melting point, so we're not worried about that. Now, this fluid cooler uses cold, and it cools fluid. So if we put water in there while it's below freezing, it makes ice. Pretty simple. This is, by the way, a positive feedback loop. You can use the ice this makes to run an ice box, and you'll get enough ice that you can keep making more and more ice and just basically turn water into ice for free. Just by using some of the ice that's made in an ice box. Just an idea. Now over here, I've used these ice cables. Ice cables are really weird because their melting point is 0 degrees C. They cannot be used to transmit temperatures above the melting point of water. That makes them pretty much useless for this setup, but fine for this setup where all our temperatures are below the melting point of water. So, and their loss is super, super low, right? So it's an alternative if you want to be really efficient and you're working with cold stuff. The other thing with heat cables is there's a redstone variant of every heat cable. So if I get, let's say, this, I meant to put it there, and turn off the sleever. It only connects to stuff when it's got a redstone signal, so you can control things with redstone. How did I get 2 wrenches? And when it is connected, you can actually read the temperature of it. So this is a circuit reader from Essentials. You can also use a comparator here, just a normal vanilla comparator. And it reads the temperature of this thing in Celsius. Now, it's probably easier and better to use the reader circuit from Essentials. That's my other mod, which Crossroads relies on, so hopefully you know how to use it. It's pretty simple. You will probably want to use a reader circuit instead of a comparator, because if you use a reader circuit, you can read numbers bigger than 15, and negative temperatures, and decimal points and stuff. But you can use a comparator if you're really only interested in temperatures between 0 and 15. There is also absolute zero with heat. There's no way to cool anything below negative 273 degrees C, aka 0 Kelvin, just like there is in real life. So there is an absolute zero. That's just a minor thing to note. So that's heat. It's all in all pretty simple. And now we're going to do rotary. Rotary is, it looks very confusing. It's often scary to people because there's a lot of numbers, but it's really not too bad, and you can absolutely do rotary based entirely on your intuition and just common sense. But the numbers are there in case you want to try and use them, and you want to try and optimize around them. So do not be scared. You're going to see a lot of numbers. Don't be scared. So let me right-click a gear, and you're going to see our first wall of numbers. Every gear, so rotary power is exactly what it sounds like. Again, it's things spin, and that's a power source. You can use that to power things. Okay? So if we have a bunch of gears here, this is a mess of gears. Let's make something a little simpler. This is one gear that's just going to spin on its own when I just crank it a little. Go. It's spinning. And we're seeing that it's got a bunch of numbers. There's a speed, there's an energy, there's a power, and there's an I and a rotation ratio. There's a lot of numbers. Let's break these down. Speed, how fast it is spinning. I, that's called the moment of inertia. You can basically just think of how heavy the gear is. Heavier gears are harder to spin fast. Like I said, you can look at the numbers or you can just use common sense, right? Energy is how much energy is in the gear, all right? Now, gears that are spinning faster have more energy. Gears that are heavier have more energy when spinning the same speed as gears that are lighter. It takes more energy to spin them the same speed, okay? Gears that are next to each other are going to balance out their speeds, right? So they're all spinning at the same speed, and they're transferring normally. Now, one thing to note is this master axis, which I haven't said anything about yet. This is just a magic block that needs to be in every gear system. So if I build a bunch of gears here, they're all going to spin together. But if I remove the axis, they don't. So every gear system just needs one of these just connected to a gear somewhere, or they don't transfer and work properly. So just a footnote that really is important and easy to forget. So you're just going to see these connected to every system somewhere. So yeah, all the gears are transmitting between each other. Pretty much what you'd expect, common sense. Gears come in different materials. This is copper, this is iron. The only real difference is this one is 125 heavy, and this is 140 heavy, right? So copper is denser than iron, so it weighs more and has a higher moment of inertia. You can decide whether you care about that or not. Usually it doesn't make a big difference. Sometimes it does. Sometimes, if you're trying to optimize stuff, it might make a difference. Axles. Axles let you connect to gears just through the center. You just connect an axle there and it spins with the gear. Gears can connect around corners. They can connect on inside corners. Oop, I placed that wrong. So connecting around corners and inside corners. They can connect sideways adjacency like you'd expect, and they can also connect through axles. So we do this. See, they're spinning together. I can have a really long axle. I can have a separate gear line which is going underneath the axle but not connected to it. So this is entirely separate, even though they are in the same block. Just pretty much whatever you'd expect. Whatever looks like it should connect will connect, and anything that looks like it shouldn't connect won't, is the rule there. So this is a bit of a mess I built earlier. Lots of axles, lots of gears. Most of them don't actually do anything. But yeah, here's a little demo. There's also large gears, and let me just grab a bronze one, sure, why not? Which are bigger and therefore heavier. And also, because they're bigger, they're going to spin slower than small gears, right? So This one's 3 times the size as this gear. It's 3 blocks across instead of 1, so when you connect them up, it spins at 1/3 the speed. And hopefully it's pretty obvious looking at it. You can see this one's spinning slower than this one, even without me right-clicking it and showing the numbers. Large gears are also quite heavy, so they usually take quite a while to get up to speed and build momentum. And I'm going to switch over to a cheat wand, which is like a hand crank, but in creative mode only, and much, much more effective. The hand crank is a very, very early game way of making rotary power. You can skip this if you want. It's just you hold right click and it very slowly winds things up. It's basically you manually turning the gear. All right. So this actually is pretty useful because if I then want 3 times the speed, okay, so this side is 1/3 the speed of this side. And now if we keep doing it, this is 1/3 the speed of this and 1/9 the speed of this. So we're doing speed multiplication, and this works both ways. So if I do this, hold on, that's wrong. If I do this, this is now turning triple the speed of this. Then they're connected together. So this is spinning 3 times as fast as this stuff is. And we can keep multiplying it. Okay. So we've also got a couple of little devices we can use to interact with redstone, because of course we do. So this is a clutch. It's like an axle, except it only connects when it has a redstone signal. So if I turn it off, nothing on this side is spinning because it's all been disconnected from the master axis. And if I reconnect it with a redstone signal, it all spins again. Okay, so it's like an axle. You can use it in the middle of a bunch of axles. You can use it connected directly to a gear like it is there. Okay, why am I placing so badly today? So we can just place one in the middle of a line of axles. Whatever you want to do, it's pretty flexible. And also, it can fit in the same block space as gears, just like normal axles can. And comparators or circuits will read the speed of it. So if I get my circuit again, so reader circuit, this thing's spinning at 2.8-ish, and it's reading 2.8-ish, right? And the other thing to note is the sign of the speed. So things that are spinning clockwise have a positive speed, and things that are spinning counterclockwise have a negative speed. So if I force this whole system to spin the other direction, if I force it to spin the other way, we're going to see that we're now reading a negative speed here. This usually doesn't make a difference. Usually negative speeds act the same as positive speeds because they're just the same thing in the opposite direction. But there's a couple things where it might make a difference, including redstone circuitry design is one of the main things. This is a way too complicated set of gears and axles just to connect to a millstone. A millstone's a pretty typical machine that uses rotary power. It runs faster the higher the speed that's connected to it is. So this thing just connects to an axle on the top or a gear directly if you want. So I can just connect it directly to a gear like this. And that's also valid. But the faster it's spinning, the faster it's going to run. We're going to cover this machine in more detail in another video. So faster it's spinning, faster it runs, and the faster it uses energy. Typically, our power sources make energy. So this is a wind turbine, very simple source of power early game, but it's a pretty bad one. Like, the maximum speed it can get to is 2 because the wind not very fast. So it'll never make a spin with a speed more than 2, ever. So if we want to power something at a speed much greater than 2 with a wind turbine, because let's say our millstone, which runs faster the speed going in is, well, we'd like to run it faster than speed 2 if possible. Well, what can we do? We can use gearing. So we put a large gear on this and a small gear on this, and we know that that means this is spinning 3 times the speed as this. So as far as the wind turbine is concerned, it might never be spinning faster than speed 2, but actually everything else that it's powering is spinning at speed 6, because we're tripling it with our gearing. And we could keep using more gears to get times 9, times 18, times whatever, times 27, sorry, not 18, whatever we want, and just keep using the gearing that way. Now this one's actually spinning at 0.8 right now instead of 2. The wind, this is very much, we'll get to wind turbines in another video. It's not a terrific power source. It's actually not enough to run this millstone right now. If we were to pull some clever trickery, we could make it good enough. But yeah, that's Rotary in a nutshell. There's a couple other really minor things. Like, for example, if I take this, these are axle mounts. They're just purely decorative. they do literally nothing. But you can just put them in the same block as an axle, and they just look like they're supporting the axle. Because some people, for aesthetic reasons, don't like the idea that they've just got giant floating rods in the sky spinning super fast, and they want them to look supported by something. So that's just a thing. They come in a variety of materials, like everything else involving gears does. Is that everything? That's pretty much everything. If you have any confusion, read the book. It's very enlightening. Hopefully that explained well. We're going to go over various machines in more detail in the next video and talk about what more things that you'd use heat and rotary power for. I just wanted to make sure to cover how they work themselves in detail. I feel like if I have to clarify anything, it's probably that I didn't explain the direction thing well. Clockwise things have a negative speed, and counterclockwise things have positive speed. While it doesn't usually come up, it might. And one little thing to mention is that's not clockwise relative to the gear. Like, if I turn this upside down, okay, this one's spinning counterclockwise relative to the gear and it has a positive speed. This one's spinning clockwise relative to the gear and it has this positive speed. It's clockwise. What it's clockwise relative to is it's clockwise relative to up. So it's not relative to the gear itself, it's relative to the positive direction, and the positive direction is up or east or south, depending on whatever you're doing, whichever way you're going. Oops, screenshot. The other thing, and this is a really common sense thing, I can manufacture a situation where it's impossible for a gear to turn. Like if I do this. This is a really easy way to just force things to break. Is if I do this, if I were to place a gear here, which way would it spin? Well, literally, there is no right answer. Because if you literally look at this, this gear would force it to spin clockwise. This gear would force it to spin counterclockwise. So in practice, it does exactly what it would do in real life, is it jams up the entire system. Like, everything stops spinning, which is exactly what would happen if you tried to build that in real life, because a gear can't spin 2 directions at once. And if I just remove the gear, everything starts spinning again. So that should cover everything. Hope that was helpful. See you in the next video. Or not. Maybe this was all you were confused on. Bye.